determine the EMF induced in the square loop in the figure if the loop stays at rest and the current in the straight wire is given by 15 amps times the sine of 2500 t, where t is in seconds. The distance A is 12 centimeters and B is 15 centimeters. We recognize that this problem requires an application of Faraday's law, and we've written Faraday's law in one of two forms. The voltage induced in a loop due to a changing magnetic field is the time derivative of the flux through that loop, and since a coil is simply a set of loops in series, the voltages of all the loops will add up, giving us a total of n times the previous result, which is the time derivative of the magnetic flux. In this problem, we have a single loop, and therefore we'll be using just the first expression. As always, the quantity flux is equal to the area integral of the field in question. Since here we're looking for magnetic flux, we're going to take the area integral of B dotted with dA. In order to perform this integral, we're going to need two substitutions, the first one of which is a formula for the magnetic field, and the magnetic field due to a straight wire is mu 0 I over 2 pi r. The second item we're going to need to perform the integral is the area element dA. Let's examine the figure in order to select our coordinate system. We recognize that the magnetic field around a straight wire will be circles that are concentric with the center of this wire, and these circles of magnetic field will form cylinders. For this reason, the cylindrical coordinate system is the obvious one for which we will integrate. The loop itself is two-dimensional, and what we see is that the loop is extended in the radius direction, and the loop exists from a radius r equals b all the way out to a radius of r equals a plus b. Furthermore, the loop is extended along the z direction. In the z direction, it's not clear where we might like to choose a z equals 0 coordinate. We're just going to select it at the bottom, and so we'll say that this loop extends in the z direction from z equals 0 to z equals a. These ranges are summarized here, and we recognize that theta equals a constant, which we might as well call 0. Because r follows a range, we're going to need a differential in the r direction, and we ask ourselves whether dr is a length, and it is. Since z covers a range, we're going to need a differential in the z direction, dz, and we ask ourselves whether dz is a length, and it is. So despite the fact that we're using cylindrical coordinate systems where the d theta would have to be changed to r d theta, our loop is extended in the r direction and in the z direction, and so the area element is very simple. It is dr times dz, and we're now ready to complete the integral. After plugging in the field and the area element, we have this expression. We still need to place limits. We're going to let the second integral be the z, and therefore this goes from 0 to a, and the first integral will be the r integral, and this one will go from b to a plus b. All constants move to the front of the integral. All items that don't depend upon z move out of that integral into the r integral, and all items that do depend upon z stay within the z integral. We'll solve these integrals in sequence. The integral of dz is z, evaluated from 0 to a, giving us a minus 0, or a, as the result of the second integral. The integral of dr over r is natural log of r, which will be evaluated from the limits of b to a plus b. Because a difference of natural logs is the natural log of the ratio, we'll have the final result for the magnetic flux, mu 0 a over 2 pi, natural log a plus b over b, times the current I. I've elected to move the current I all the way to the back of this expression because I recognize that when we need to find the voltage by taking a time derivative, it's the current that depends upon time. Using the substitution of the expression given, we have exactly the previous result, except the I has been replaced with 15 sine of 2500 t. Therefore, we're able to solve for the voltage of the loop by taking negative the derivative of the flux with respect to time. We ignore the constants and recognize that the derivative of sine is cosine, and by the chain rule we need to take the derivative of the interior, and the derivative of 2500 t is 2500. Plugging values into this expression, we can do the algebra, and the result is that the voltage in this loop is negative to 5.29 times 10 to the minus 4 cosine omega t. And that completes our Faraday's law derivation.